just looked at a giant skyscraper or a massive bridge and thought to yourself, how in the world is that even standing? Well, it turns out there's a kind of secret rulebook, a blueprint for reality itself that explains how all of it works. And today, we're going to start flipping through it. I mean, just look at this thing. A crane like this can lift weights that just seem impossible, like it's totally defying gravity. But it's not magic, it's engineering. The real mystery is, how do we get from a simple pile of metal to a machine that can predictably, reliably build our entire world? How is that even possible? Well, the answer to that question, it lies in this incredible field of science called engineering mechanics. And this isn't just a bunch of abstract theory. No. This is the actual toolbox that lets us understand, predict, and ultimately build the impossible. So what exactly is mechanics? Well, at its very heart, it's the science that deals with forces and motion. I mean, think about the chair you're probably sitting in right now. Mechanics is what explains all the forces working together to hold you up, to keep that chair from just collapsing. It's the foundation for pretty much every piece of engineering you can see. Now, in the story of mechanics, you've basically got two main characters, statics and dynamics. Think of statics as the master of things that stay still. A bridge, a building, anything that's in perfect, balanced equilibrium. Dynamics, on the other hand, is all about the action movie stuff, right? It's about accelerated motion, a rocket taking off, a race car screaming around a corner. One is all about stability, the other is all about change. And, these ideas aren't new. The principles we use today were built up piece by piece over literally thousands of years. It goes way back to minds like Archimedes, figuring out something as simple as a lever. Then, centuries later, you get Galileo, who's obsessed with pendulums and watching how things fall. And then came the big one, Isaac Newton, who basically took all those pieces and put them together into the laws we still use today. Okay, so to really get a grip on the rules of mechanics, first we've got to learn the language. And believe it or not, it all boils down to just 4 basic ingredients. Everything we're about to talk about is built from these 4 simple but incredibly powerful ideas. And here they are, the absolute fundamentals. You've got length, which just tells us where something is, time, which tells us when, mass, which is a measure of how much stuff something is made of, and force. Well, that's any push or pull. What's kind of mind-blowing is that with just these 4 quantities, we can describe pretty much any physical thing happening in the entire universe. Now, engineers have some clever tricks to make the math a whole lot easier. They're called idealizations. The first one is the idea of a particle. So imagine you're trying to calculate the Earth's orbit around the sun. Do you really need to know the exact shape of every mountain and valley? Of course not. You can just pretend the entire planet is a single point that has mass. It's a brilliant shortcut that lets you focus only on what's important for the problem you're trying to solve. The other big idealization is the rigid body. With this one, we basically assume that an object, say a steel beam in a building, doesn't bend or stretch at all when you put a load on it. Now, look, in reality, everything deforms a tiny, tiny bit. But for most big structures, that change is so small, we can just ignore it. And that assumption makes the analysis way, way simpler. All right, we have our ingredients. We have our clever shortcuts. Now, it's time for the main event. These are the absolute, non-negotiable, unbreakable rules of the physical universe, laid out by Isaac Newton more than 300 years ago. This is the bedrock of all mechanics. Newton's first law is basically the law of inertia. You can think of it as the universe's default mode. Things just want to keep doing whatever they're already doing. If an object is sitting still, it's going to stay still. If it's moving, like a hockey puck on perfectly smooth ice, it's going to keep moving in a straight line at the same speed forever, unless some other force messes with it. The second law. Now, this is where things get interesting. This is where the action is. It gives us this really clean cause and effect relationship. If you hit an object with an unbalanced force, you will cause it to accelerate. You push it, it speeds up. And the beautiful part is, it's not random. It's a direct, predictable, totally measurable relationship. And that relationship is captured in what is, quite possibly, the most important equation in all of classical physics. Force equals mass times acceleration. F equals ma. I mean, don't let how simple it looks fool you. Our entire modern world is built on this little formula. It's the secret code that lets us calculate everything from a satellite's path to how to design a safe car. And finally, we have the third law. For every action, there's an equal and opposite reaction. This is such a cool concept. It means that forces never exist by themselves. They always come in pairs. When you're leaning against a wall, you're pushing on the wall, right? Well, the wall is pushing back on you with the exact same amount of force. It's a perfect, beautiful symmetry. Newton also gave us this law of universal gravitation, which explains the attractive pull between any two objects with mass. For us here on Earth, the most important version of that is the force pulling us down towards the center of the planet. And we have a special name for that force. We call it weight. This is why an astronaut weighs less on the moon. It's not because they have less stuff, their mass is the same. It's because the moon's gravity is weaker. So we've got the laws. But to actually use them to build things, engineers all over the globe had to agree on a common language. They needed a standardized way to measure everything, so an engineer in one country and an engineer in another were speaking the exact same mathematical language. And the number one most important rule of that language is something called dimensional homogeneity. It's a fancy term, but it just means you have to compare apples to apples. Every single part of your equation has to be in the same units. You can't add meters and seconds. And this isn't just about being tidy. This is a fundamental safety check that prevents real-world disasters. Now, what's really fascinating here is how the two major systems are built. You've got the SI system, which most of the world uses. It starts with length, time, and mass as its basic units, and then it derives the unit of force, the Newton, from F equals m. But the US customary system does it the other way around. It defines length, time, and force, the pound, as its base units, and then it derives the unit for mass, which is called the slug. They're just two different ways of getting to the same result. Okay, so we've got the concepts, we've got the laws, and we've got the units. So how do engineers actually put it all together to solve a real problem? Well, it isn't just randomly plugging numbers into formulas. There's a structured, reliable process to it. And this is basically it. It's a beautiful, logical method. You start by really, truly understanding the problem. You draw it out, you visualize it, then you apply the principles we've been talking about, you turn them into math, you solve it, and then comes the most important step of all. You step back and you use your professional judgment to ask, does this answer actually make sense in the real world? That right there, that's the heart of good engineering. So let's boil it all down. If you walk away remembering just 4 key things, make it these. 1. Mechanics is the science of forces in motion. 2. Newton's 3 laws are the absolute fundamental rules of the game. 3. Your mass is constant wherever you go, your weight changes depending on gravity. And 4. The key to solving any hard problem is using a logical step-by-step approach. So there you have it, the fundamental blueprint of our physical world. You now understand the basic rules that govern everything, from a simple baseball in flight to the tallest skyscraper on Earth. So I'll just leave you with this one question. Now that you know the rules, what problem would you solve?